My name is Dave Stokes. On Twitter, I'm at Stoker. My email is david.stokes@oracle.com. I am a MySQL community manager and have been so 11 years next month. The MySQL community team used to be all over at various shows, including All Things Open on a regular basis. And I do miss being there in person. It's a wonderful group. I've seen the show grow from a couple hundred to a couple thousand. Hopefully next year we'll all be in Raleigh. Before I go further, let me talk about this slide. Oracle is very paranoid about stuff being overpromised. Now, the stuff that's already out there and been released, including 8.027, our newest version of MySQL came out today. It's got some very interesting new features there. But the stuff that's going to be in 8.028 and other stuff coming out, I don't have a good knowledge of. So whatever I talk about on future products, if I get off on a tangent, please take with a grain of salt. I might misspoke, so please don't hold me to that. So, by the way, if you're running MySQL 5.6, the end of life for that was February 5 of this year. So please upgrade, hopefully to MySQL 5.7, or even better yet, MySQL 8.0. By the way, I will talking about 8.0 today and the free to download community edition. If I get up on the enterprise edition, I should remind myself to denote that the enterprise edition is not free. You have to buy a subscription for that. Okay, if you want to try the new MySQL data service, this is the folks that actually pay me to do this sort of talk. If you want to try it out for free for 30 days, you can get $300 in credits to try it out. If you stay to the lower end configurations, $300 will last you quite a long time. If you want to try the high availability cluster, we have a 3-node InnoDB cluster set up for you. That goes a little bit faster. If you're trying the high-end analytics engine along with the which is called HeatWave, along with the autopilot machine learning algorithms, it goes a little bit faster, but it is free credits if you want to give it a try. Okay, so what are we talking about today? Well, nobody complains when the database is fast. Well, they complain, but usually not about the database. And when you start having queries running slower and slower, it kind of gets into the Harry Potter dark arts type thing. It's not really anything magical. It's very simple engineering. And the trick is to give better information to the query optimizer. And I'll show you how to do that. Now, the trick is you have to understand how to speed up queries, and it's not magic. If you go to sites like Stack Overflow, DBA Stack Exchange and all that, there's a lot of stuff that's built up over the past 25 years of MySQL's life that's mythology and myth and practices that might have been good 15 years ago, but aren't good now. So I'm going to walk you through the proper uses of indexes, histograms, hopefully get into locking options and some other ways to speed up your queries. The slide deck, as I mentioned earlier, is set up for a 2-hour workshop. So there's a lot more material in there that I'm going to be able to cover. By the way, this is a dry subject. We're talking saltine cracker in the middle of the Sahara Desert on a September sunny afternoon. It's a lot of text on screen. I wish there was a better way to do this with interpretive dance. That way I probably wouldn't be able to do it. Once again, the slides are available at slideshare.net/Dave Stokes. And if you're starting off on this, you're fairly new to databases and you're just getting the query tuning, don't try to absorb this all at once. This is something you have to play with, work with, and go from there. And by the way, work on your most frequent query first, because if you have something that runs 10,000 times a minute and you take a 1/10 of a millisecond off that, that adds up. If you speed up something that normally runs in 5 minutes and it runs in 4 minutes and 55 seconds and you only run it once a quarter, not much of a win. And by the way, these optimizations that you're going to be making will change over time as your data usage patterns, as the size of your data changes, as your data structures change. Now, today, I'm not covering a lot of stuff. System configuration. I'm not going to go in how to configure your operating system. I'm not going to go into configuring MySQL. Best advice there is set your InnoDB buffer space size to 75% of physical RAM and leave it there. I'm not going to talk about hardware. That's a weak subject in itself, talking about all the various ways things can be configured and misconfigured. Also, not talking about the cloud. That's something that I'm not going to broach. Also, I'm not covering how to normalize your data. For those who don't know, normalizing your data is where you break it down to the smallest component parts, so you minimize duplication. Duplication is bad because it wastes disk space. Also, if you have the same piece of information in two places and you're only updating one, that other piece of information that's not getting updated, not being kept current, is a time bomb. I recommend using the third normal form or better for normalization, and to get around where you dive into an index to another table, to an index to a table, to another table, using a JSON table for stub data. Also, you need to think about the way you're going to use your data. And by the way, if you have questions, please throw them up. Oh, someone wrote Merlot. That caught my eye. You don't use a fork to eat soup. So if you're studying time series data, you probably don't want to set up like a transactional system for selling t-shirts or something like that. Badly normalized data will hurt the performance of your queries. And the analogy I like to give is you have a racetrack near your house for horses, and you want to participate in that, but you only have a dachshund. The dachshund just does not have the capability to beat a thoroughbred over 1.1 miles. So the main thing we have to be concerned about today is the optimizer. And I like to consider that as kind of the brain and nervous system of the entire database. Now, query optimization is a feature of most relational databases you'll find out there. And the query optimizer wants to find the most efficient way to get the data that you're requesting. And we'll talk about how we measure that in a minute. This is one of the hardest problems in computer science on how to optimize all this stuff. It's actually harder than writing an operating system. Now, most optimizers are cost-based these days. And this came around in the original days of the database, in that disk drives were extremely expensive, extremely slow, and reading from disk was 100,000 times slower than reading from memory. So the worst cost you could do was having to read stuff off disk. And most cost-based optimizers use that, although there's some stuff going on now that disks are faster and there's near memory like disk drives. You're going to see some of that change over the next couple of years, probably. Now, a lot of this is predicated, or the optimizer is predicated on some knowledge about your data. And we'll talk about that a little bit. And the more detailed the statistics are for the optimizer, the better your chances are going to be to have a good query plan. Now, the query optimizer takes a look at your query. It comes out of the syntax checker to make sure you put things in the proper format and are calling the stuff you're supposed to do. And once again, it's looking for the cheapest way to do that. And it's kind of like a GPS. It knows where your sales table was as of the last time it was accessed, and it knows how many rows are in there as of the last time it was accessed. Now, like a GPS, the historical information is fairly useful. Now, at lunch today, I went left out of the driveway, right at the stop sign, over the railroad tracks, and went to my favorite restaurant. But sometimes the historical information that's locked in here on my GPS is wrong. I could have had my neighbor flood out the street. The stop sign could have been gone. The railroad tracks might have been blocked by a train, and the restaurant might have relocated. So historical information is great, but having up-to-date data is a lot better. Now, the final determination of what the optimizer puts out is called the query plan, and I'll show you how to get that. As a side note, MySQL wants to optimize your query every time it sees it. Other databases like Oracle, once you get a good query plan, you can lock it down, and until the data changes or the hardware changes or some other thing happens, you don't need to have it re-optimized. However, MySQL, being helpful, wants to redo it every time. And we'll talk about a little bit how to get around that later. So if you have 5 tables you're trying to join together, the optimizer has 120 different ways of arranging that. That's 5 factorial. So you can see how this can escalate and become a problem rather quickly when you have a lot of options. Now, the heart of all this is using explain. And this is something else I could probably run a 2-week class on. Maybe I'll talk about this next year at ATO. And explain requires a great deal of explanation. I've been told this is a little bit hard to read. I've got to redo this. This is the syntax for explain. If you fire up the MySQL shell and type in \help explain, you'll see the syntax. What you're basically doing is you're prepending the word explain to your query. And before MySQL 5.7, it only worked on select statements. So if you have a delete, you had to actually change delete to a select and run it that way. Now, of course, to make this even more complicated for you is that we have lots of different varieties of explain, just to make your life more interesting. So let's take a look at some of those. If we run explain by itself, in this example, we have a simple query. We're going to select wildcard from the table city where the country code is equal to Great Britain, or GBR. And I prepend explain here, put in the \G instead of a semicolon, which prints it out vertically instead of the tabular format. And it comes out and gives me some information. So there's our query. This is the details on how the query is executed. And I'm going to skip over that for now. But down here on the bottom, this is the actual query, the query plan that the optimizer wants the server to run to bring back your information. As you see here, it's expanded this wildcard to all the column names in the table. Now, MySQL Workbench has something called Visual Explain, which is great for documentation. And it comes out and tells us some information like the cost of the query, how many rows it has to read, tells us it's doing a non-unique key lookup on the city table using the country code column. Now, if we do a slightly different query with format equals tree, it gives us some more information, a different type of information. So explain format equals tree. This time we're looking for everything from the city table, but we're joining that table to the country table where the city.population column is equal to the countries.population table. So we're looking for the city, state, nation type thing. And it'll come back and give us information like it's using a hash join. Tells us how it's joined, the cost, the number of rows, and how it does the query. Now, if I want even more information, I can run that query with format equals JSON, and it puts it out in a JSON format, and it gives me a lot more information like the number of rows examined, the cost of reading, the cost of doing the evaluation, the data read per join. It's kind of like you might only need 2 records, but it's going to go out there and grab an entire block of records to bring back those 2. Now, something we added a little bit over a year ago is explain analyze. All the previous explains use historical information. Well, that's good, but what if you want the real stuff? Well, explain analyze actually will run your query. The great thing about this is you find out what really goes on with your query. Bad news here is that if you have a really substantial query that sucks up a lot of resources and you're running this during production time, you may not win some friends. By the way, if you run explain and then explain analyze and see a skew in the times between the predicted and the actual, run analyze table on your tables to get that corrected. It will update the statistics there. So we're going to skip away from explain for just a little bit and go on to something just a little different. What are indexes? Well, according to Wikipedia, a database index is a data structure that improves the speed of data retrieval. That's not going to get you a good answer on Jeopardy. And mainly there are ways to quickly get to your data. And I like to think of an index as a table with shortcuts to another table. So it's a very cut down version of your original table with a pointer to those records. By the way, the more indexes you have, the slower things can get. Indexes take up memory. Databases love memory. Also, we'll talk about some of the overhead in just a moment. And of course, to make things even better for you folks just learning and to steepen that learning curve, we have many types of indexes at MySQL, as do most other relational databases. I'll skip over this syntax for creating an index. You can create an index with create index. You can do it with your create table statement or with an alter table statement. By the way, MySQL uses something called a clustered index. All the records you put into MySQL are sorted by your primary key. And it's stored in that order. It's a very fast way to look up stuff. In the Oracle world, this is known as an indexed organized table. So for best performance, choose the primary keys carefully on performance critical queries. Modify them or changing them at a later date is very expensive and very messy. So don't really want to do that. Let's go on. So this is the mental image I'd like you to have, where you have this little index where it has pointers to the actual data over here. So if you're looking for record number 6 in the index, it puts you right to the row that you want to go to. So it's a good mental image to have it as a small, fast table pointing to a bigger table. In reality, MySQL being a clustered index, it sorts everything by the primary key. Now, secondary indexes, which are indexes on other columns, are very handy and very useful, and you'll see how to make those in just a minute. And the secondary indexes actually store the pointer to the primary index for that record or records. So if you have a primary key that's very long, adding secondary indexes on that use up more space, and you can actually run yourself out of space. So the best advice is have the shortest primary key you have reasonable, and then use short secondaries if you can. So let's create a table with a primary key. Very simple table, create table T1. You notice I'm very creative with these table names and column names. Column 1 is an integer, not null, auto increment. That means every time we add a record, this will be incremented by the server. And 2 varchar columns 2 and 3. Now, an index is a list of all the keys that are out there. So key is for the row, and the index is all those rows put together. And in MySQL, you'll hear key and index commingled, used interchangeably. We also do that with database and schema. Just have to get used to that. Now, the primary key is hopefully uniquely defined for a row and should be immutable. Don't go around changing it later. It's really messy. Now, InnoDB needs a primary key because it's that clustered index. It wants a way to how to sort it. And if you don't specify one, it will pick one for you. And guess what? It's probably not going to be the best value. If you can, don't use null values. We'll go into that a little bit later. By the way, the folks who are fans of UUIDs, UUIDs are not a good idea for a primary index. If you really have to do that, we have a function called UUID to bin. Otherwise, avoid them. The big trouble is MySQL likes to have things incremented by ones or a preset number to keep things ordered. UUIDs do not monotonically increase, so that kind of makes them a bad choice there. Now, something else you can do is you can index on the prefix of a column. So rather than getting the entire column indexed, we're just going to take a sub part of that, subsection of that. In this example, we're taking on the customer table, we're taking the name field and just indexing the first 10 characters. Works really great if you have a lot of long names, and you can identify down to probably 5 or 3% of the proper records with that. However, if you're in an environment where the last names are all 3 or 4 characters, doesn't buy you a whole lot. Also, you can index multiple columns. Now, in this example here, we have a table that we have a last name and first name. And we're going to index and call the index name on the last name field and the first name field. Now, this index is great for searching on last name and first name or last name. It will not be picked up by the optimizer if you're searching on just on the first name. So if you're doing something like year, month, day, it'll work for year, month, day, year, month, or year. It won't work for month, day, or just day. So when you're creating these multiple column indexes. In the first slot here, put the most unique, fewest number of records, whatever you want to call it, in that first position, and go on as you add more and more columns. Another alternative is if you have data that doesn't really work well for multi-column indexes, might want to create a hash on that. It's works sometimes. In this example, we're just making a hash by taking the two values, concatenating them together, and then doing an MD5 hash on that. And of course, we have other types of indexes out there, unique indexes, which is hopefully what your primary keys will be, full text indexes for searching words out of bar, car, and car fields, covering indexes, which is one of my favorite. If you need 3 pieces of information for your query and they're all in your index, you don't need to dive into the data to go out there and get there. It's actually a faster way to get stuff. I talked about secondary indexes already. Spatial indexes, this is for geographical information. So if you want to know all the places to get pizza within the radius of your current longitude and latitude, this is the type of index you would use for that. Now, we also have functional indexes, which is a way to work with part of the data in a column or a derived value based on information from that column. In this example here, we're going to create a table for birthdays, and we have the name of the person and their birth date, which is in we're going to store as a date data type. And we're going to create an index on just the month of the birthday. And if we insert a record into here, inserted birthdays value 1, Mac, that's my other dog, and their birthday. When we go to do a search on it, we search, select star from birthdays where the month of the birthday equals 12. The optimizer will go out and actually tells us, aha, I'm using that functional index to find the date that we want. Another interesting thing with functional indexes is, say like you have a business where you have a product that has a cost of goods sold and another cost for shipping, and a customer comes through and they want to buy something where the total cost plus shipping is less than 100. So what our query here goes out there, and the optimizer says, oh, I can use this index that we created on the cost plus shipping and find the records that I want faster. Now, the only caveat here is you can see the original query you just saw on the left where we have cost plus shipping, and it uses the index. But on the right-hand side, notice we have shipping plus cost. Order does matter, and in this case, it has to do a table scan. Table scan means it has to read the entire table. It's kind of like reading an entire data file to find that one row in there that you want. It can't, it's better to go to the index. Although in this case, you'll notice the cost is much lower here than over here, but as the table grows in size, this will pay off in the long run. Something we added with the JSON data type is that we don't have an array data type. So a lot of folks started using our JSON data type for arrays. And the problem up to this time was that you could have a one-to-one correlation between a row in the table and an entry in an index. Well, when you have arrays, you need more than one entry in there. So in this example here, I have an array with these numbers and the word Mo, and I want to find out is 3 is a member of this array, and it will actually tell me 1, which is yes. So we know that that fits in the value. So big rule number 1, always have a primary key on your InnoDB tables. InnoDB is the best storage engine we have. If you're still using MyISAM, please convert over. We've done a lot of optimizations over the past 5 years that have really, really sped this up. So always have a primary key. As I mentioned earlier, if you don't pick one, InnoDB will pick one for you, and it won't be what you want. So how do I find tables that don't have indexes? Well, this is a handy little query that actually goes out to the information schema, and it goes through its statistics. The only caveat here is make sure your system has been up and running for several days, weeks, if not longer, so the historical information is actually valid. If you do this right after a reboot, there's no statistics there, or there may be no statistics there, and the information you're going to get back are not going to be useful to you. What if you need to add an index but can't change your queries? This is indicative, especially in the PHP world, of I hate to say WordPress. I don't want to blame everything on WordPress, although a lot of people would. So you have a query inside your application, and you don't want to change the application that says select star from table Y. Now, you don't have a primary key there, but you'd like one to have things sped up. What you can do is alter table, add column. We're just going to call it K for some reason. And we're going to call it invisible. And we also designate it as our primary key. This way, you don't have to change the old code, but you've updated your tables and things are going to be a little bit better organized. So MySQL has two main types of index structures. And they are B trees, as you see over here, where you're able to do a binary search down to your data, and hash joins. These came out a little bit over, almost 2 years ago. So if you're doing an equijoin where you're, where price equals, like the earlier version where city.population equals country.population, what it does is it reads in one of the table and then hashes the other ones on top of that, and everything that meshes together and outputs to you. Much faster. You don't have to turn it on. It just gives you the queries by much faster, and the optimizer knows how to do that. So some other things to keep in the back of your mind. If there's a choice between multiple indexes, MySQL will default to the smaller of the indexes, the one with the smallest number of rows, because it thinks it's most selective. May not be true. MySQL will use indexes and columns more efficiently if they're declared the same type and size. By the way, varchar and char are considered the same thing, but if you're doing a varchar 15 to a char 10, there's some casting has to go on, but a varchar 10 to a char 10 are okay. By the way, check to make sure that you're using the same collations and character sets. That really also speeds things up. Okay, a few words on null. For those of you who are new to databases, null is kind of a different concept. Back in the early days of computers, they used 1 for true, 0 for false. And the idea was you had all these binary circuits that were either on or off, 1 or 0, great. But what about the cases when you didn't know the value of a piece of data? It can't be marked as 0 because that'd say it's false, can't be marked as 1 because that'd be true. So they needed a third value, which they decided to call null. And that has caused a lot of problems ever since. So null values are a mess to index. So if you have a lot of very nicely tailored, say like serial numbers for your product, and then some nulls in there, it really slows down the performance of the indexes. It's kind of like a junk drawer where it's very hard to search through. And by the way, as I mentioned earlier, sometimes you can create an index that covers just the right amount of columns so you don't have to dive into the data. This is called a covering index. I mentioned that a little bit earlier. So here's an example. We want to find out the customer ID, the total sales, the sales ID from the customer order table, where the customer ID equals 101 and the sales ID equals 7, and they've actually bought something that costs more than 1 unit. Now, if we want to do this without indexes, it has to go through and read everything and then pull out the records we don't want. And if we run this through Visual Explain, we'll see that our cost is 1.5. Now, if we index the customer ID and the sales ID, and we rerun this, the cost drops from 1.5 to 0.7. So that's 46% better. That's pretty good. Now, this is on a very small data set. Larger data sets, you'd see much more performance increase there. Well, let's go through and index customer ID, sales ID, and the total, which are the 3 pieces of information we're looking for. And we've gone from 1.5 to 0.7 to 0.66 with this, which is 44% faster and 6% over the last version. Now, this sort of thing is what DBAs do on a regular basis. They're looking to carve off fractions of milliseconds. Now onto invisible indexes. This was an idea that when I first heard about it, I was kind of confused, and then it was explained to me that in the days before invisible indexes, you'd have a query and you'd wonder if the index was really helping you and you weren't sure. So you run explain. And of course, that index was not helping you and you'd remove that index. Well, as you're rerunning explain, you start getting phone calls, text screams from power users that their query is suddenly slow. And suddenly realize that that index in question may have had no use for you, but the rest of the planet seems to need that query badly. So you take seconds, minutes, hours, days, weeks to rebuild that index. Well, with invisible indexes, you have an index, you're not sure if it's any good. You check it with explain, doesn't do anything for you. So you make the index invisible. The optimizer for the entire server cannot see that index. As you're rerunning explain, you start getting the phone calls, texts, and screams, and you just make the index visible again. You don't have to go back and rebuild it. And this time you have to figure out, well, are you gonna blame this on the network, JavaScript, GDPR, Slack, cloud, whatever option you have for that. By the way, this schema will show you which indexes have not been used, so you can give those candidates for removal, but be cautious. As I mentioned earlier, you might not have built up enough statistics to tell you enough to be useful. Making an index invisible is real easy. Alter table, alter index, make it invisible. To reverse it, visible. I'm not going to go on to this. By the way, with Workbench, it will tell you which database schema statistics, which indexes are unused. They're taking up space and memory, so you can get rid of them. You can also find out that same information with this query. Pull it off the slides, please. And by the way, you can check for tables that aren't using indexes to find the ones that are using full table scans. Now, sometimes full table scans are not bad, like you're doing the quarterly reports and you have to go through all the customer information. You're going to read everything in that table. But if you're doing quick, so like sales information, transactions, that's a bad sign. So on to histograms, and I am running low on time. So what is a histogram? Well, here's an example. Someone went out and measured the height of 10,000 US females. And you see this nice little bell-shaped like distribution here, and that is a histogram. And with MySQL and other databases, the histogram helps the optimizer find the most efficient query plan. Now, usually histogram is an approximation of the data distribution within a column. And MySQL by default will assume the data is evenly distributed within a column, which is not a good thing all the time. And as Jonathan Champ says, blame it on the cloud. So we have two types of histograms with MySQL, singleton and equiheight, and I'll show you what those look like. And the maximum number of buckets you could have is 1,024. I like to think of this as putting your data into logical buckets. Now, histograms are used mainly for non-indexed or indexable columns. It's created once on demand, so there's no overhead. When the table is modified, the histogram kind of loses a little bit of its sheen and its value. It's easy to rerun this, put it in with a cron job or a MySQL event. So it's good, but not for data that churns. Now, why would you want a histogram instead of an index? Well, with an index, every time you do an insert, update, or delete, you have to change that structure that you saw the picture of earlier. Sometimes you have so much action on a table and it's clustered around one part of the nodes of the table of the B tree or the B plus tree, that things start getting contentious and they start slowing down. If you're doing a ton of inserts, it slows things down. Also, occasionally the optimizer will double check the statistics by doing index dives, and those usually don't happen at convenient times for you. So the optimizer occasionally fails to find the most efficient query plan. And it's basically because it's making assumptions about your data. And it wants to know things like how many rows are in each table, how many distinct values are there in each column or the cardinality, and how is the data distributed in each column. And that's where histograms really come into shine, is the distinct values and the distribution. So Equiheight histograms. One bucket represents a range of values. Think of last names. You have people line up A to G, H to L, M to T, and U to Z. And then we have singletons, where a bucket represents a single value, or it could be a range of values, but it's usually a single value. So in this example here, we have 3 buckets, 101, 102, and 104. Don't know what happened to 103. We create a table called histograms. We put in 2 101s, 3 102s, and 1 104. So here's our data, 2 101s, 3 102s, 1 104. And if we create a histogram on this data here, and then we take a look at it on the system, it knows that the value of 101 is 1/3 of all the data in the table. Values 102 and below are 83% of the data, and 104 and below is 100% of the data. So if we come in there and say, give me all the values less than 105, the optimizer knows that it has to go out there and grab all the data. Now, this is another way to look at those statistics. The value of 101, cumulative frequency, is 1/3 of our data. With 102 and 101 together, that's 83% of our data. And with 104, that's 100%, as I mentioned earlier. So this actually gives the optimizer enough information to know better of what it has to go out there and grab off the disk or memory to answer your query. Real easy to create a histogram, analyze table, update, and there's no create, just there's update histogram. And in this case, we're histograms on 3 different columns, each with 10 buckets. If we want to update it later, we're updating 2 of those. We can change the number of buckets there. And you can actually drop a histogram if you want. Now, if you want more information about histograms, it's out there. Information schema will tell you the data type, the bucket count, the column name, and the schema that you're coming from. Now, here's an example where you see where histograms shine. We have a similar table where we have 2 1s, 3 2s, and 4 3s out there. And if we look at our data, we get the counts of the various pieces of information. Now, without a histogram, remember we have 9 rows, and we're asking for all the values from that table where X is greater than 0. Now, the optimizer at this point doesn't have a lot of information, doesn't have any information because we just created it. And the optimizer will say, okay, I'm going to make a wild guess that I need to read 33.32% of the table to get the information. And I know there's 9 rows out there. If you ever worked with a building contractor or an auto mechanic who's giving you a bad estimate, you know how expensive that can be. So in this example, it says, yeah, I only have to read 33% of those 9 rows, but we know all the values are above 0. So this is a case where the optimizer is kind of making a bad guess. By the way, the filtered row, the closer you get that to 100, the better you are. So let's create a histogram out there, 3 buckets, and we run our query. Now the optimizer knows to get X greater than 0 that it has to read all the rows. So this is a much better estimate. If you also run it with explain and analyze, you see that it knows that it has to go out there and grab the 9 rows. So performance is more than indexes and histograms. And by the way, I got about a minute before I'm going to go to questions and answers. There's other things out there. You'll have to read through this on the slides. But one of the things is once you start playing with databases, you start looking for things that happen when from explain, where you see there's file sorts, table scans using temporary tables that you can try to work away from. Also, you kind of get a code smell-like idea where you see if the join orders look right. And then you start working on the configuration of the server and the hardware. 2 other things I like to mention is locking options. Previous, if you wanted to lock something, it would wait for that data to become available. If you have skipped lock, which is something that came out with 8.0, if those rows are locked, it will skip over those. And we also had no wait. So if it comes back and you want it to return right away, so you can go off and look for other options. In this case, we're looking for seats at a concert. It comes back immediately. Other things that I'm not going to go over are resource groups and optimizer hints, although they're really interesting. So big question is, does it work? So use explain to get information on a query before you start making changes. Know the available indexes out there that are already established, so you don't have to reinvent the wheel. Make one change at a time and keep comparing performance, and hopefully you're getting the performance gains that you want. Eventually you get to the point where you hit diminishing returns or you're sick of it. And by the way, note somewhere what you've been doing and why you've been doing that. If you're really into this, I recommend these two books by a former colleague of mine. And Query Performance Tuning is, if you had to buy just one, I'd recommend that. He writes in a very nice, relaxed style. And I'm on my third reading of that particular book and still picking up new information. Very well done book. The Concurrency one is great for if you're into transactions. Another book that is unfortunately aged, it covered up in MySQL 5.5. There's supposedly a new edition coming out, but not by the original author, so I don't know anything about it other than that. If you're working with the JSON data type, please take a look at my book. This has a lot of programming examples, best practices, and basically teaches you the ins and outs using JSON within a relational database. If you're in a startup, Oracle would like to help you with some marketing exposure and some credits. Please go to oracle.com/startup. And with that, let's go to questions and see what we have. Once again, the slides are at slideshare.net/Dave Stokes. I posted them last Monday for another show. And like I said, it's 2 hours worth of information. I just covered in a little bit over 40. So any questions?
Great session, Dave. Definitely enjoyed it. Definitely enjoyed the session with you. There was a question in the chat asked by Jay. He was saying, would empty strings be better than nulls?
Yes. Empty strings would be better than nulls.
All right, so I'm still checking to see if anyone wants to ask any questions. You can go ahead and drop it in the chat, or you can use the Q&A feature. Okay.
I use Postgres and was hoping this would translate over. Is it transferable? For the most part, we do things just a little bit differently, but the concepts of indexes and histograms are pretty much the same. So it's kind of like I taught you how to drive a stick shift, but now you're in an automatic. So a lot of it's there, but some other things you don't have to worry about.
There's another question in the chat. Jonathan is asking, are the index dives the reason that sometimes a query that has been running finds spikes in duration?
Sometimes, yes. I'd say probably about 70% of the time. The other part of the time, it could be that there's something else going on at the server, but index dives do affect you. Well, yeah, I have to say, if you're too shy, email me, ping me on Twitter. I'm fairly easy to find. And I am writing a book on this subject. So hopefully next year I'll have them in hand at the booth in Raleigh. And Crystal Williams Brown, good luck with the research. It can lead you down some interesting rabbit holes. Well, thank you all for attending. I know this is the last session of the day, so please go out and enjoy your evening, and see you next year.